Module 4, Lecture B, Expansion Binning. By the end of this lecture, you will be able to, first, use binarization and discretization to convert continuous features into thresholded or binned representations. Second, generate polynomial, interaction, and spline features for nonlinear modeling. And finally, build leakage-safe preprocessing stacks using transformers inside pipelines. Thresholds and bins. Threshold-based binarization. Threshold-based binarization turns a continuous numerical feature into a simple yes or no indicator by checking whether it crosses a chosen cutoff. This can make data easier to interpret and help models capture sharp changes in outcomes around meaningful boundaries. It is most useful when crossing the threshold matters more than the exact value. Threshold-based binarization turns a value into a simple category based on whether it crosses a chosen cutoff. This can match real-world decisions, such as meeting a minimum income or exceeding an activity limit. But it removes information about how far the value is above or below the threshold. It works best when the cutoff is supported by domain knowledge or evidence, not chosen arbitrarily. Choosing the right threshold is important because it affects what the model learns. Thresholds can come from expert knowledge or from patterns in the training data, but they should be set using only the training data to avoid data leakage. In some cases, one cutoff is not enough, and multiple bins may better represent the feature. When used carefully, threshold binarization creates clear, interpretable features that reflect real-world decision boundaries. Python code. Threshold-based binarization. This example shows how binarization converts spending values into simple threshold indicators. Each value is checked against a cutoff, and the result compares the original feature values with their transformed binary form. We import NumPy for efficient numerical work with arrays, Pandas for organizing and analyzing data in data frames, and Scikit-Learn's binarizer for converting continuous values into binary values using a chosen threshold. We create a NumPy array of annual customer spending amounts, arranged as a column vector, with one value per row. This format makes it easy to evaluate each spending amount individually against a threshold in later transformations. Set a spending threshold of $1,000, then use Scikit-Learn's binarizer from the preprocessing module to convert each customer's spending into a binary value. The result shows whether each customer spent more than the threshold. A binarizer converts the spending data into simple 0 and 1 values using a $1,000 threshold. The fit transform method applies this rule consistently, marking amounts above the threshold as 1 and all others as 0. The result is an integer binary array showing which spending amounts exceed $1,000. We verify that the transformed data has the same number of rows as the original data to protect data integrity. If the row counts differ, an error is raised to signal a problem in the transformation. This check helps ensure the process is consistent and reliable. A small Pandas data table is used to compare original spending amounts with their transformed values. One column contains the spending values, and the other shows whether each amount is above $1,000. This makes it easy to inspect the binary transformation alongside the original data. The output begins with a message explaining that spending values are being converted into binary indicators using a $1,000 threshold. The results are then printed in a clean string format without row numbers, making it easy to compare each original value with whether it is above the cutoff. This script converts customer spending amounts into a simple binary label using a $1,000 threshold. With Scikit-Learn's binarizer, each value becomes 1 if it is above the threshold and 0 otherwise. The results are shown in a Pandas data frame alongside the original spending values, making it easy to identify customers who spend more than $1,000 annually. Discretizing continuous features. Discretizing continuous features means turning many numeric values into a few meaningful ranges, such as age groups. This can make patterns easier for models to detect and interpret, especially when the relationship is not linear. For example, sales may change sharply after a temperature threshold, while further increases have less effect. Discretizing continuous features means grouping numeric values into ranges so models can capture changes that happen across intervals, rather than treating every small increase as equally important. This is useful in areas like credit risk or healthcare, where categories such as income bands or cholesterol levels may be more meaningful than raw numbers. It can also reduce the influence of extreme values, but it loses detail because values in the same group are treated as the same. When discretizing data, choose bin boundaries carefully and make sure they fit both the data and the modeling goal. Bins may come from domain knowledge or from the data itself, but poor choices can add noise or hide important patterns, especially with skewed data. To avoid overly optimistic results, decide on bins using only the training data, while balancing interpretability with the detail in the original values. Python code, discretizing continuous features. This example shows how continuous temperature measurements can be discretized by grouping raw values into bins. The result makes it easy to compare the original temperatures with their binned interval features. We import NumPy for numerical operations and pandas for working with tabular data. We also import the k-bins discretizer from Scikit-Learn, which converts continuous values into discrete bins for data analysis and machine learning tasks. We create a NumPy array of Celsius temperatures, ranging from 12 to 36 degrees, stored as floating point values. This gives us a simple continuous feature for demonstrating how continuous data can be divided into bins. The temperatures array is reshaped into a two-dimensional feature matrix, so it can be used with Scikit-Learn transformers. The reshape method automatically sets the needed number of rows and creates one column, making the data compatible with the next transformation step. Before transforming the temperature data, the code verifies that the array has 9 rows and 1 column, meaning there are 9 measurements in the expected format. If the shape is incorrect, it raises an error to stop the process. This check helps ensure the discretizer receives valid input and prevents transformation problems. A Scikit-Learn bin discretizer can convert continuous temperature values into 3 discrete groups. Using ordinal encoding, each group is represented by an integer, and with a uniform strategy, the bins have equal width across the full range of values. The discretizer learns bin edges from the temperature data, then assigns each temperature to the appropriate bin. The resulting bin labels are converted to integers and flattened into a one-dimensional array for easier use. We retrieve the bin boundaries learned by the discretizer using the first stored set because there is only one feature. Then we create an empty list to hold clear labels for each bin, so the value ranges are easier to interpret. The process creates readable labels for temperature bins by looking at each pair of neighboring bin edges. Each boundary is rounded to 1 decimal place, then combined into a short-range description in degrees Celsius. These descriptions are added to a labels collection for later use. A pandas data frame is used to show how continuous temperature values are converted into discrete bins. It includes the original temperatures, the bin number assigned by the discretizer, and a readable label for each bin's range. This makes it easy to see the mapping from each temperature to its corresponding interval. The code displays the learned temperature bin edges, rounded to 1 decimal place, so the created intervals are easy to read. It then shows the first 5 rows of the result data frame, illustrating how original temperature values were assigned to bins. This gives a quick check of how continuous temperatures were converted into discrete categories. This script shows how to turn continuous Celsius temperature values into categories using Scikit-Learn's K-bins discretizer. The temperatures are reshaped into the required 2-dimensional format, then divided into 3 equal width bins based on the data. Each value is assigned a bin number and a readable temperature range, making it easy to compare the original measurements with their discrete categories. Choosing bin strategies. A binning strategy decides how continuous data is grouped into categories for a model. Equal width binning splits the full range into intervals of the same size, which works well when the scale is naturally meaningful, such as ages or temperatures. But with uneven data, like household incomes, many values may fall into only a few bins, while others stay empty, making it harder for the model to capture useful variation. Equal frequency, or quantile-based binning, creates bins with roughly the same number of observations, giving the model balanced categories. It is useful for representing relative position, such as income levels or lab value percentiles. The trade-off is that bin ranges may be uneven and less intuitive, so small changes in dense areas can move a case to a new bin, while larger changes in sparse areas may not. Good binning should reflect both the data's distribution and the real-world meaning of the feature. Domain knowledge can guide useful cutoffs, but bins should be chosen using only training data to avoid leakage. The goal is to use enough bins to capture important patterns without adding noise or overfitting, balancing interpretability and model usefulness. Python code. Choosing bin strategies. For a skewed feature, equal width and quantile binning can produce very different results. Equal width bins use fixed value ranges, while quantile bins aim for more balanced counts across bins. Comparing the bin counts and boundaries helps show how each strategy handles the skewed distribution. We start by importing tools for data work: NumPy and Pandas for numerical data and data structures, and Scikit-Learn's binning tool for converting continuous values into discrete intervals. This setup supports binning, which helps categorize data so different binning strategies can be analyzed and compared. We create a NumPy array of income values measured in thousands, using a skewed distribution to reflect a more realistic income pattern. The data is then placed into a Pandas data frame with one income column, making it easier to analyze and manipulate with Pandas. Before binning the income data, the code confirms that the data has the expected shape, 12 rows and 1 column. If not, it raises an error to stop the process. This check helps ensure the data is properly formatted before transformation. We use Scikit-Learn's K-bins discretizer to split the data into 4 equal width bins. Each bin is encoded as an integer, and the uniform strategy divides the full data range into evenly spaced intervals. This is useful when consistent bin spacing matters more than having the same number of data points in each bin. Quantile binning divides data into bins with roughly the same number of observations. Here, the Scikit-Learn K-bins discretizer is set to create 4 bins, using ordinal encoding, so each value is replaced by an integer bin label. The quantile strategy forms the bin boundaries from the data distribution to keep the bins balanced. The income data is grouped using 2 binning strategies. Equal width binning places values into evenly spaced intervals, while quantile binning creates bins with roughly the same number of observations. In both cases, the transformed results are converted to simple integer labels and flattened, making it easier to compare how each method distributes the income values. We count how many observations fall into each bin for both equal width and quantile binning. Using NumPy's bin count function with a minimum length of 4 ensures every bin is included, even if it has no observations. These counts let us compare how the two binning strategies distribute the data. Round the bin edges from both the uniform binner and the quantile binner to 1 decimal place to make the boundaries easier to read. This makes it simpler to compare how each method divides the data range and shows how they differ in handling the distribution of values. Income values are measured in thousands of dollars. The narration compares two binning strategies: equal width bins, which split the numeric range into evenly spaced intervals, and quantile bins, which aim to place a similar number of observations in each interval. By showing the bin boundaries and counts for each method, it highlights that equal width binning preserves consistent interval size, while quantile binning balances the data across bins. This example shows how binning choices change the way a skewed income dataset is represented. Equal width binning splits the income range into 4 evenly spaced intervals, which can produce very uneven counts. Quantile binning shifts the boundaries, so each of the 4 bins contains a more similar number of observations. The key point is that binning strategy strongly affects how skewed data is summarized and interpreted. Feature expansion. Polynomial feature expansion. Polynomial feature expansion helps linear models capture curved relationships by adding terms such as squared or cubed effects. This is useful when changes are not constant, such as costs rising faster as parts age or sales gains tapering after more advertising. In short, it lets a linear method learn curves and turning points without manually designing a curve. Polynomial expansion helps models capture nonlinear patterns by adding transformed versions of existing features. For example, squaring temperature can help represent energy demand changes on very hot or cold days, while home size, dosage, or age may have effects that vary across their range. These added features are especially useful when the learning algorithm does not automatically model nonlinear relationships. Polynomial feature expansion can help models capture nonlinear patterns, but it should be used carefully because it can quickly add complexity. High-degree features may overfit noise, especially with small or imperfect datasets. And scaling is important because polynomial values can become large. In practice, use domain knowledge, validation, regularization, or model selection to add only the flexibility the model truly needs. Python code. Polynomial feature expansion. Polynomial feature expansion adds squared features so a linear model can fit curved patterns. This lets the model move beyond a straight line and better match nonlinear trends. We import the main tools needed for numerical work, visualization, and modeling. NumPy supports data manipulation. Matplotlib handles plotting, and the Scikit-Learn version helps with compatibility checks. From Scikit-Learn, we use linear regression for training linear models, a pipeline tool to combine processing steps, and polynomial features to let those models capture nonlinear patterns. We create a NumPy random number generator and seed it with 42 so it produces the same random values each time the code runs. This makes the example repeatable, which helps with debugging and sharing consistent results. The data simulates machine maintenance costs based on age. Machine ages are generated from 0 to 10 years, and random normally distributed noise is added to represent real-world variation. The maintenance cost follows a quadratic pattern, with a base cost, a linear age effect, and a stronger curved increase as machines get older. The code verifies that the machine age data and maintenance cost data have the same number of entries. If they do not match, it raises an error, ensuring every input has a corresponding target value before model training begins. We create a linear regression model in Scikit-Learn to learn the relationship between machine age and maintenance cost. Training the model finds the best fitting straight line by reducing the gap between predicted and actual costs. This means the model can capture only linear, straight line trends in the data. We build a pipeline that first expands the machine age data with polynomial features, adding both the original feature and its square to capture a curved relationship. A linear regression model then uses these expanded features to learn how machine age predicts maintenance cost. Fitting the pipeline applies both steps together: feature expansion followed by model training. We create a smooth range of machine ages from 0 to 10 and use it to compare model predictions. The linear model produces a straight-line estimate of maintenance costs, while the polynomial model uses expanded features to produce a curved estimate. Plotting both over the same age range shows how each model fits the data. Access the polynomial feature step in the pipeline to inspect how the original age feature was expanded. By asking for the output feature names, you can see the new polynomial terms created from that feature. This helps clarify how the transformation changes the model's input structure. The code reports the Scikit-Learn version, then compares the number of features before and after polynomial expansion. It starts with one input feature, machine age, and shows how polynomial transformation creates additional features. It also prints the expanded feature names, helping explain how the model's inputs have changed and how much complexity has been added. This plot compares observed maintenance costs with two regression fits based on machine age. The data points are shown alongside a straight linear fit and a degree 2 polynomial fit, using clear axis labels and a legend to distinguish them. The main purpose is to show how polynomial expansion lets linear regression model a curved relationship rather than only a straight line. This script shows how polynomial feature expansion helps linear regression model curved patterns. It creates synthetic maintenance cost data with a quadratic relationship to machine age, then compares a basic linear model with a degree 2 polynomial model. The linear model can only fit a straight line, while the polynomial model adds squared features so it can follow the curve more closely. The output also reports the Scikit-Learn version and shows how the original input features are expanded. Interaction features. Interaction features let a model learn when the effect of one input depends on another. This matters because many real-world relationships are not simply additive, such as when property value depends on both size and neighborhood, or when exercise affects blood pressure differently by age. Adding interactions helps models capture patterns that basic linear models may miss. Interaction features help models capture how variables work together, not just their separate effects. For example, electricity demand may rise especially on days that are both hot and humid, and exam performance may depend on both study time and prior preparation. These features can combine numerical or categorical data, helping models learn more complex patterns across different groups or situations. Interaction features can make models more expressive by capturing meaningful nonlinear relationships, but they also add complexity and can introduce noise. As feature counts grow, possible interactions increase quickly, making models harder to train, interpret, and generalize. They are most useful when guided by domain knowledge or exploratory analysis, such as combining related factors in finance or manufacturing to reveal important patterns. Python code, interaction features. This example shows how interaction features can improve linear regression by allowing one feature to change the effect of another. The model scores are then compared to see how performance differs with and without these interactions. We import key tools for building and evaluating a machine learning model. NumPy supports numerical work and random number generation, while Scikit-Learn provides linear regression, R-squared scoring, train test splitting, pipelines, and polynomial feature creation. Together, these tools let us train a linear model, test it on unseen data, streamline the workflow, and capture more complex feature relationships. We create a small, reproducible dataset to model a target that depends on an interaction between two features. A fixed random seed is used. Then one feature is generated with values from 50 to 200, and the other from 1 to 10, with 120 samples each. These two features represent area and quality, and their combined effect is the key pattern the model needs to learn. The price is generated from a base value, with added effects from area, quality, and their interaction. Random normal noise is then added to make the prices more realistic and unpredictable. Finally, the area and quality values are paired into a two-dimensional feature array, preparing the data for analysis or modeling. The code verifies that the feature matrix has 120 rows and 2 columns, matching the expected dataset structure. If the dimensions are incorrect, it raises a clear error so data preparation problems can be caught early. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function. The features in target, such as area, quality, and price, are divided so that 25% of the data is reserved for testing. A fixed random state makes the split reproducible. This helps prevent data leakage and allows the model to be evaluated fairly on data it has not seen during training. We build a basic linear regression model in Scikit-Learn using the original training features, without adding interaction terms. After training the model, we test it on unseen data and measure performance with the R-squared score, which compares the model's predictions with the actual target values. We build a pipeline that adds interaction features before fitting a linear regression model. It uses Scikit-Learn's polynomial feature generator with degree 2 to capture pairwise interactions, while excluding squared terms and the bias term. This lets the linear model represent more complex relationships between features without adding higher-order effects. The interaction model is trained by fitting a pipeline that creates interaction features and applies linear regression to the training data. It is then tested by comparing its predictions with the actual target values using the R-squared score. This interaction score shows how well the model performs when interaction features are included. We can inspect the polynomial feature step in the pipeline to see what new feature names it created. By asking that step for its output feature names using the original inputs, area, and quality, we get the expanded feature list, including interaction terms. This helps show how the original features were transformed. This section checks the Scikit-Learn version for reproducibility, then compares the original training features with the expanded set that includes interaction terms. It also reviews the expanded feature names to show how those interactions were created. Finally, it compares R-squared scores with and without interaction features to show whether they improve model performance. This script shows how interaction features can improve linear regression. It creates synthetic price data based on area, quality, and their combined effect, then compares a basic model with one that includes the area and quality interaction. Using test set R-squared scores, the interaction model usually performs better, showing that feature combinations can capture relationships the original features miss. The script also reports the Scikit-Learn version and the expanded feature names to highlight the added interaction term. Spline feature basis. Spline feature bases model continuous inputs with smooth, local curves instead of forcing one straight line or an overly complex global curve. They split a feature's range using knots, then connect the regions smoothly, so the model can capture changing patterns while keeping predictions stable. This helps represent effects like medical risk changing with age, without the overfitting risk of high-degree polynomials. Spline bases help linear models capture smooth, nonlinear relationships in data. They let predictions change flexibly, such as when square footage, temperature, or commute time has different effects at different levels. This gives a model more realistic behavior, while keeping it easier to train and interpret than many more complex methods. Spline features work best when their flexibility and knot locations are chosen carefully. Too few knots can miss important nonlinear patterns, while too many can overfit noise, so knots should be placed using meaningful values or the training data distribution. To avoid bias, spline transformations should be learned only from the training data. Used properly, splines provide a strong way to model nonlinear relationships and capture subtle trends. Python code, spline feature basis. This example shows how spline features help linear models capture curved patterns. It compares predictions made with raw features to predictions made with spline features. This setup imports the main tools needed for a regression workflow. NumPy handles numerical arrays, Matplotlib supports visualization, and Scikit-Learn provides the modeling utilities. The workflow uses linear regression with spline feature transformation in a pipeline to model nonlinear patterns, splits the data into training and testing sets for fair evaluation, and measures performance with mean squared error. A fixed random seed is set to make the results reproducible. Then, 120 evenly spaced values from 0 to 10 are created and reshaped into a single column feature array for later model processing. Random noise is generated from a normal distribution with mean 0 and standard deviation 0.25 to add variability to the data. The target is then created by combining a sign pattern in the input with a small linear trend and the added noise. This produces a smooth, nonlinear relationship with some randomness. To evaluate the model fairly, the dataset is split into training and testing parts using Scikit-Learn's train-test split function. 25% of the data is kept for testing, while the rest is used for training. Setting the random state to 42 makes the split reproducible each time the code runs. We start by creating a Scikit-Learn linear regression model, then train it with the input features and target values. During training, the model learns the best linear relationship by choosing coefficients that reduce the difference between its predictions and the actual targets. A pipeline combines a cubic spline transformation with linear regression to model more complex patterns in the data. The spline uses 6 knots and excludes the bias term. Then, the full pipeline is fitted to the training data, so the transformation and regression are learned together in one step. The training data is passed through a spline transformer in the pipeline, turning one original feature into several spline-based features, so the model can learn nonlinear patterns. The output also reports the Scikit-Learn version for reproducibility, then compares the original single column with the expanded number of columns after transformation. We evaluate both the linear and spline models on the test data, using root mean squared error. For each model, we compare its predictions with the actual target values, compute the mean squared error, and take its square root. The two results are then rounded and printed, so we can easily compare which model performs better on the test set. We create a smooth range of input values from 0 to 10, and use it to generate predictions from both models. The linear model produces a straight-line prediction curve, while the spline model produces a more flexible curve. Comparing these curves helps show how each model behaves across the input range. This visualization compares training data with two model fits for a nonlinear relationship. A scatter plot shows the observed input and target values, while two curves show the predictions from a linear fit and a spline fit. The plot includes a clear title, axis labels, and a legend, so the data and both fitted models can be easily distinguished. This script shows how spline transformations help linear regression model nonlinear patterns. It creates noisy curve data, splits it into training and test sets, then compares a basic linear regression model with one that first converts the feature into spline features. The spline-based model usually achieves a lower test error because it can fit curves rather than only a straight line. A final plot compares both predictions, showing the spline model following the data's curved shape more closely. Safe pipeline transformations. Custom function transformers. Custom function transformers let you include domain-specific preprocessing directly in a machine learning pipeline. This keeps transformations, such as preparing timestamps or adjusting trip distances, applied the same way during training, validation, and deployment. By making these steps part of the pipeline, you reduce errors and improve consistency and reliability. A custom function transformer should behave like any other preprocessing step. It takes data in, applies one clear operation, and returns data in a consistent format. This stable interface is essential for reliable pipelines, whether the transformer computes financial ratios, adjusts skewed data, or extracts state features. Each transformation should preserve the expected inputs and row alignment, avoid hidden assumptions from training data, and remain easy to review, debug, and explain. Custom function transformers should be placed inside pipelines to prevent data leakage and keep preprocessing consistent. This ensures transformations that learn from data are fitted only on the training set, then applied unchanged to validation or test data, including during cross-validation. As a result, feature engineering remains reliable, and model evaluation and deployment are more trustworthy. Python code, custom function transformers. This section shows how to use custom transformers within safe machine learning pipelines. The key idea is to fit preprocessing only on the training folds, so information from validation data does not leak into the model. It also compares this leakage-safe approach with manual feature engineering. This setup imports the main tools needed to build a machine learning workflow. NumPy and Pandas handle numerical data and data frames, while Scikit-Learn provides tools for preprocessing, splitting data, training a logistic regression classifier, and measuring accuracy. A pipeline combines preprocessing and modeling into one streamlined process, with column-specific transformations, custom transformations, and feature standardization included as needed. We create a small, reproducible customer dataset with 240 records by using a fixed random seed. Customer incomes are generated from a normal distribution, centered around $60,000, then limited to a realistic range between $25,000 and $120,000. Monthly debt is generated as a randomized share of each customer's income, so higher income generally leads to higher debt, but with variation. Additional random noise is added to make the values less uniform. The final debt amounts are then limited to a realistic range, from $100,000 to $50,000. The process estimates customer risk by comparing each customer's debt to their income, then adding a small amount of random variation to reflect real-world uncertainty. If the resulting risk score is greater than 0.32, the customer is labeled high risk. Otherwise, they are labeled not high risk. This creates a simple binary classification based on debt to income level and simulated noise. We organize the income and debt data into a pandas data frame so it can be handled efficiently. We also define labels that indicate whether each customer is high risk, based on their debt-to-income ratio. Together, these features and labels prepare the dataset for later processing and modeling. The code first verifies that the customer data has the expected shape, the correct number of rows, and two numeric feature columns, income and debt. If the structure is wrong, it raises an error explaining that two numeric features are required. This early check helps prevent later pipeline failures by confirming the data is in the expected format before transformation. We split the customer data into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is kept for testing, while stratification preserves the same proportion of high-risk labels in both sets. A fixed random state makes the split reproducible across runs. The add debt ratio function turns the input data into a table with income and debt columns, then creates a new feature by dividing debt by income for each entry. It returns this result as a one-column table called debt to income, capturing how much debt each entry has relative to its income. This function sets the output feature name for a custom transformer. It accepts the transformer and optional input feature names, then returns a single feature name, debt to income. This helps keep feature names clear and consistent when data is transformed in a pipeline. We wrap the custom debt ratio calculation in a Scikit-Learn FunctionTransformer so it can fit into a machine learning pipeline. The transformer uses the add debt ratio function for the transformation, skips input validation when the data format is already trusted, and applies a custom feature naming function so the output is labeled correctly. This makes the custom feature engineering step easy to combine with the rest of the pipeline. A ColumnTransformer is set up to apply a custom debt-to-income ratio transformation only to the income and debt columns. All other columns are dropped, so the pipeline receives only the newly transformed feature for the next processing steps. A pipeline combines preprocessing, feature scaling, and logistic regression into one consistent workflow. The scaler normalizes features to have a mean of 0 and a standard deviation of 1, while the model uses fixed settings for reproducibility and convergence. Keeping these steps together helps prevent data leakage and ensures the same process is applied during training and testing. The pipeline is first trained on the training data, learning both the needed transformations and the model parameters. It then applies those same transformations to the test data and uses the trained model to make predictions. Accuracy is measured by comparing those predictions with the true test labels, showing how well the model performs on new data. We preview the transformed features by applying the pipeline's feature transformation to the first 3 rows of the test data. The results are rounded to 3 decimal places and converted to a simple list, giving a quick check of the debt-to-income ratios for those customers and confirming that the transformation worked as expected. The code checks the Scikit-Learn version for compatibility, then reports the pipeline's test accuracy as a quick measure of performance. It also previews the first few debt-to-income ratios from the test data and confirms that the custom feature transformation was applied correctly inside the pipeline during fitting and prediction. This example shows how to build a safe Scikit-Learn pipeline with a custom feature transformation. It creates customer income and debt data, adds a debt-to-income ratio through a custom transformer, then applies scaling and logistic regression. The model is trained and tested on separate data, with output showing the Scikit-Learn version, test accuracy, and sample ratios. The main point is that placing the custom transformation inside the pipeline helps prevent data leakage between training and testing. Reversing transformations. Reversible transformations help keep preprocessing workflows clear and reliable. When data is changed for modeling, such as through logging or standardizing, it can become harder to relate results back to real-world values. Reversing the transformation restores the original scale for prediction and interpretation, while reusing the same training parameters to keep the workflow consistent. To reverse a transformation correctly, you must use the same information learned during the original fitting step. For example, standardized data should be restored using the training set's original average and spread, not values recalculated from new data. Pipeline transformers help by separating what is learned from how it is applied, keeping transformed features consistent and evaluations reliable. Some data transformations cannot be fully reversed, so preprocessing pipelines must make these limits clear. Scaling or monotonic changes can often be undone, but binning, rounding, or simplifying values may permanently remove detail, such as an exact age or sensor reading. In these cases, reversal can only return a range or representative value, not the original data. Clear pipelines help distinguish original from transformed values, supporting consistent evaluation, communication, and safer deployment. Python code. Reversing transformations. This example shows how to reverse fitted scaling transformations to recover values in their original units. Pipelines store the training parameters safely, and the printed results let you compare the original values with the recovered ones. The script imports key tools for data preparation and machine learning. NumPy supports numerical array operations, while Scikit-Learn provides utilities for splitting data into training and testing sets, building processing pipelines, and standardizing features. Together, these imports prepare the script to manipulate and transform data effectively. We create a small NumPy array of income values to keep the example easy to follow. Each value is placed in its own inner list, making a two-dimensional array with one column, which matches the input format commonly expected by Scikit-Learn. The income data is split into training and test sets using Scikit-Learn's train-test-split function. Two entries are held out for testing, and a fixed random state makes the split reproducible. This treats the test set like future, unseen data that is not used during model fitting. We build a pipeline with a StandardScaler to normalize the income data by centering it and scaling it to unit variance. The scaler is fitted only on the training data, where it learns the mean and standard deviation to reuse later. This keeps transformations consistent for new data and prevents information from the test set from leaking into training. The test income data is first scaled using the pipeline's transform method, which applies the same mean and standard deviation learned from the training data. Then the inverse transform method converts the scaled values back to their original units. This makes the results easier to interpret on the original data scale. Fitting a new standard scaler on the test income data is a form of data leakage. It uses the test set to calculate scaling values, such as the mean and standard deviation, before evaluation. Because the test data should remain unseen, this can make model performance look better than it really is. This example checks the Scikit-Learn version, then shows how a pipeline uses the training data mean to scale test income values. It compares the original test incomes, the scaled values, and the recovered values after reversing the transformation. It also shows what happens when a scaler is fit directly on the test data, emphasizing that transformations should be learned from the training set to avoid data leakage. This script shows how a Scikit-Learn pipeline can scale data and then recover the original values. The StandardScaler is fitted only on the training income data, so the test data is transformed using parameters learned from training rather than from the test set. The inverse transformation restores the original test values, confirming that the scaling can be reversed. It also demonstrates data leakage by showing that fitting a separate scalar on the test data would improperly use information from the evaluation set. Preventing data leakage. Preventing data leakage means making sure evaluation data does not shape training decisions. A common source is preprocessing, such as scaling, binning, or imputation, when these steps use the full dataset before the train and test split. This lets information from the test set influence the training features and can make model performance look better than it really is. To avoid data leakage, include preprocessing within the model training process. Fit transformations only on the training data, then apply the learned settings unchanged to validation or test data. This keeps steps like imputation or binning from using information outside the training set, giving a more honest estimate of performance on new data. During cross-validation, model selection or tuning, it is important to prevent data leakage because training and validation splits change repeatedly. Any preprocessing, such as setting thresholds or scaling, must be learned only from the training portion of each split, not from the full dataset. Pipelines help by refitting these steps within each fold, keeping validation data unseen until evaluation, and producing more trustworthy performance estimates. Python code, preventing data leakage. This example contrasts leaky preprocessing with a safer approach. Using pipelines ensures transformers are fit only on the training folds, and cross-validation scores help show the risk of data leakage. The script imports NumPy for numerical work with arrays and Scikit-Learn for machine learning tasks. It also brings in Scikit-Learn's classification data generator, which creates a synthetic dataset for demonstrating the machine learning workflow. We import 3 key tools from Scikit-Learn: logistic regression for binary classification, cross-validation scoring to evaluate model accuracy across multiple data splits, and pipelines to connect preprocessing and modeling steps. Using a pipeline helps apply transformations consistently during evaluation and reduces the risk of data leakage. The script uses Scikit-Learn's k-bins discretizer to turn continuous numerical features into discrete bins. Here, it applies quantile-based binning and outputs the result in a one-hot encoded form. This can help certain machine learning models use the data more effectively by representing distribution patterns as categorical features. We create a small synthetic classification dataset using Scikit-Learn's make classification function. It contains 600 samples with 4 features, where 2 features help determine the class labels and 2 do not. A fixed random state makes the dataset reproducible, and the function returns the input features along with the target labels to predict. The code first verifies that the feature data has the expected size, 600 rows and 4 columns. If the dimensions are wrong, it raises an error to stop the process. This check helps ensure the data is properly structured before modeling begins. We use Scikit-Learn's k-bins discretizer to convert continuous features into discrete categories. It creates 5 quantile-based bins and represents them with dense one-hot encoding, so each bin becomes its own feature. The discretizer learns the bin edges from the data for use in later preprocessing. The features are first discretized, turning continuous values into bins before cross-validation begins. A logistic regression model is then evaluated with 5-fold cross-validation on these transformed features. Because the discretization was fitted outside the cross-validation loop, information from the validation folds may leak into training, making the performance estimate unreliable. A Scikit-Learn pipeline is used to keep preprocessing safely inside each cross-validation fold. It first applies binning with 5 bins and 1 hot dense encoding. Then fits a logistic regression model with a fixed random state and up to 500 iterations. Because the binning is refit only on each training fold, this setup helps prevent data leakage and keeps cross-validation valid. We evaluate the safe pipeline with 5-fold cross-validation in Scikit-Learn. Because the pipeline includes both the discretizer and logistic regression model, the discretizer is fitted separately within each training fold. This prevents information from the test fold from influencing the binning process, giving a more reliable estimate of accuracy. The example first reports the Scikit-Learn version to support reproducibility, then compares mean cross-validation accuracy for 2 preprocessing strategies. The leaky approach fits the discretizer before cross-validation, while the safer pipeline approach refits it within each fold. The main lesson is that preprocessing should be fit inside the pipeline to avoid data leakage and produce more reliable model evaluation. This script shows why preprocessing must be handled carefully to avoid data leakage in machine learning. It compares a leaky method, where discretization is learned from the full dataset before cross-validation, with a safer pipeline method that refits preprocessing inside each training fold. The leaky approach reports higher accuracy because it uses information from data that should be unseen during training. The pipeline result is a more trustworthy estimate of real model performance, reinforcing that preprocessing should be fit only on training data. In this lecture, you learned to use binarization and discretization to convert continuous features into thresholded or binned representations, generate polynomial, interaction, and spline features for nonlinear modeling, and build leakage-safe preprocessing steps using transformers inside pipelines. In the next module, Module 5, we will go over categorical's missingness.
Thank you for your attention. See you all in the next lecture.